Section 10.3 is the convergence of series with positive terms. So just a key note here, right, as I've been kind of mentioning in class, we are coming up with techniques for determining convergence and divergence. And in this section, we are specifically looking at positive series that are growing as n approaches infinity. All right, so integral here. This is a test that we're going to definitely use. Let a sub n equal the function with respect to n. So think of it more as a function and not just a sequence or series. Where f of x is positive, decreasing, and continuous for x is greater than 1, greater than or equal to 1. So those three circumstances have to be true. If the integral from 1 to infinity of f of x dx converges, then the summation of a sub n also converges. Right? So the space, the unbounded area, comes to a finite answer. Then the summation comes to a finite answer. If the integral from 1 to infinity of f of x dx diverges, then so does the summation there. So I wrote myself a little note. Again, the positive, the decreasing, and the continuous are important. They have to be true in order for us to use this. And I wrote the unbounded area, right, because it goes to infinity under the graph, converges. Just putting it in word form for myself. Then S converges. So this first series that we're looking at is called the harmonic series, and it's a common one. So like once we've proven it here, you're then going to use this quite frequently. It's used again throughout this section as like known fact. Okay, you don't have to constantly reprove the harmonic series every single time. So it's the summation from 1 to infinity of 1 over n, and we want to show that it diverges. So first of all, we know that it is positive and continuous for values greater than or equal to 1, right? 0 is the only issue. And then what we can do is show that it is decreasing. How would we show something is decreasing?
If the derivative is negative.
Perfect. Good, Simon. So we need to actually do that. It's kind of crazy. We haven't done stuff like that recently, but we're going to bring that back in. So f prime, right, so if f of x is equal to, oh, I'm sorry, I was jumping ahead. I was looking at example 2, but it's the same idea. F of x is equal to 1 over x, which is x to the negative 1. So I can derive it without the quotient rule. So I would get negative x to the negative 2, or negative 1 over x squared, which is negative, right? It's a negative numerator over an always positive denominator. So it is positive and continuous and decreasing. And something as simple as that, we could actually even visualize the graph, and we know that that branch up in the second quadrant is a decreasing branch. All right, so, yep, go for it.
So we can't use this for when a function is like below the x-axis ever, even if it's getting closer. Like if you reflected what you have in the first quadrant down to the fourth,
well, what you
still can.
I think what you could do, and I think the question would allow you can pull the negative out, right? If it's just a simple coefficient out in front, you can pull it out in front of your summation, and then inside of your summation, your series is now positive, right? If it's just the true coefficient. Like if I had negative 1 over x here, well, I could take the negative out, and then I would deal with 1 over x, and then apply the negative at the end. So it would be okay. Okay. So all I've done so far is said, yes, my integral test applies. So therefore, I can take a look at the integral from 1 to infinity dx over x, right? Which is equivalent to, some of this extra notation you don't always have to use, but I'm going to make sure I put it there at least early on. It's equivalent to the limit as r approaches infinity, 1 to r, dx over x. And we know the integral of 1 over x is just ln. So then this is equal to the limit as r approaches infinity of ln x from 1 to r, which inside of here, when I do my f of b minus f of a, I have ln r minus ln 1, which is just 0. So just for space, I'm just going to notate that real quick. This is equivalent to ln r. Which, if we take the limit as r approaches infinity of ln r, it goes to infinity. So because this integral diverges, then this series also diverges. So therefore, S sub n diverges. So integral test is make sure it's positive, continuous, decreasing. We test it. If it diverges, then it diverges. If it converges, then it converges.
Do you have to use this test, or can you use different ones? You can do it without calculus.
Yeah, no, that's fine. Listen, Tyler, unless the problem tells you which one to use, this chapter is all about use your skills. We're offering more options, but yeah, if you are confident that, and especially if it's a multiple choice, right, do whatever's fast enough for you to get the answer, okay, with confidence. All right, example. All right, so this is the one that I was looking at before when I was talking about getting that derivative. This one's more important because it's not as obvious, but it is positive, right, because the numerator is positive, the denominator is squared, so it's positive and continuous right off the bat for values greater than or equal to 1. And we will get our derivative real quick to prove that it is also decreasing. Right, so f of x is equal to x over x squared plus 1 squared. So therefore, f prime is 1 times 2 times quantity x squared plus 1 to the first times the 2x minus x. Oh my gosh, I'm rushing. Let me go back. X squared plus 1 squared minus x times what I just said, 2x squared plus 1 to the first times x squared. Go over x squared plus 1 to the fourth. Okay, so canceling out, cubed, first, that factor's gone. Guys, somebody has some background noise. If you don't mind muting or turning that off for us. All right, so when we combine like terms here, it will go to a negative 3x squared plus 1 over an x squared plus 1 cubed. Okay, so for values greater than or equal to 1, the denominator will remain positive, but the numerator is negative. So this is less than 0 when x is greater than or equal to 1. So if the derivative is negative, then the function is decreasing. And again, this is all just background work so that we can use our integral test. So now we can say the integral from 1 to infinity of x over x squared plus 1 squared dx, right, is equal to, this is equal to the limit as r goes to infinity. But in order to do the integral, we need to do some u sub work. So limit as r approaches infinity of 1 to r, x over x squared plus 1 squared dx. All right, so my u is the x squared plus 1. My du is the 2x dx. 1/2 du is then x dx. So I would have, and I also need u of 1, which would be 2. I don't have to do it for r because r is infinity, so manipulating infinity is not going to do anything. So now I go from 2 2 to infinity. And my integral becomes a 1/2 du over u squared. And that would anti-derive. I would have limit as r.
But just to confirm.
Yep.
You changed it from 1 to infinity to 2 to infinity because you added a 1/2, right?
No, because I did my limits of integration in terms of u. I keep my 1/2. I know some of you guys put it somewhere else and deal with it that way. That's fine. But this 1 became a 2 because u is x squared plus 1. So u of 1 is 1 squared plus 1, or 2.
Okay, got it. Thank you.
Yep. So when I anti-derive this 1/2 over u squared, I have a negative 1/2 u to the negative 1 from 2 to r. And I'm taking the limit of that as r goes to infinity. So I end up simplifying here. Limit as r goes to infinity. I have a negative 1 over 2r plus a 1/4. Right, so now if I do the infinity, this fraction, the negative 1 over 2r, zeroes out, and I am left with a 1/4, so I converge.
So there's no point of like substituting it back.
Substituting what? Oh, getting back to the x. I wouldn't do that, no.
Okay,
No.
Okay.
No. Whenever you use u sub out of good practice, you should commit to your u and not go back.
Okay. Got it.
Okay?
Why did you do the blue part?
Because remember, in order to use integral test, you need positive, continuous, decreasing.
Okay, and then we just established that it was
It's a negative.
negative.
And positive, continuous, decreasing for values greater than or equal to 1. Right, so it's positive, it's negative for those values.
Oh, yeah.
Okay. All right. Theorem 3. Convergence of p-series. So 10.2, example 1. 10.3, first slide. Okay. So the infinite series from 1 to infinity of 1 over n to the p power converges if p is greater than 1. Right? And diverges otherwise. Make sense? Think about that. If you manipulate your exponent to an exponent like a fractional exponent, or like a fractional exponent would make your denominator not grow as large, so it's not going to end up converging to 0. Or if it were a negative exponent, then it would reciprocate it. Okay? Comparison test. Assume that there exists an m greater than 0. Right? So we assume that, and we pick it sometimes when we're proving things, such that a sub n is larger than or equal to 0, but smaller than or equal to b sub n for n, little n, greater than or equal to m. So all of that will carry through and help us when we are kind of manipulating things to figure out what to compare. If b sub n converges, right, b is the bigger one, then a would converge. Okay? If a diverges, then b is going to diverge. These theorems, they make sense when you see them by themselves, but you really have to pause and think, okay, which one's bigger? What conclusion did I come up with? Does it fit it? Does it make sense? So there's going to be times when you try to go and prove something, but you have the mismatching information, right? You proved that the larger one diverged, which doesn't prove that the smaller one diverges. So you have to go back and change the change the comparison essentially. Okay, so example 3, does the summation from 1 to infinity of 1 over root n 3 to the n converge? Okay, so for n values greater than or equal to 1, we can make this inequality up. So I'm going to call this a sub n, which is 1 over root n, and 1 over 3 to the n is my bn, and the way it's written, a is smaller than b. Okay, so this one's pretty straightforward because b is geometric, r is less than 1, therefore it converges. Converges because geometric with r less than 1. So then, by comparison, the smaller one must converge, is all that I'm saying. And then, therefore, if they both converge, then the whole thing converges.
I just want to curious.
Yep.
Why did you write that 1 over root n is less than 1 over 3 to the n?
Yep. Because that's
Like,
it.
If n is equal
Oh,
to 1.
I meant to write. I'm sorry. I meant to include the whole thing in there.
Oh,
Oh, okay.
okay.
Sorry.
Yeah,
Thank you for asking, Ann.
yeah.
Yeah. A sub n is the original. B sub n is just the portion of it, and that portion is geometric, which does converge. All right, we've got 4 more examples. Okay, does S, which equals the summation from 2 to infinity of 1 over n squared plus 3 to the 1/3 converge? So here I'm going to use that harmonic series. I'm going to show that 1 over n is less than or equal to our given. And this only has to be true for n is greater than or equal to 2 because that's what the summation is. So anytime we start with an inequality, I'm showing one fraction, start with fractions, is smaller than the other, I can make kind of the reciprocal, the opposite statement. Right, if I cube both, if I take this and I manipulate more, and I cube both, so I'm not looking at a cubed root anymore, and I remove the fraction, so I'm kind of like cross-multiplying, but it would make this statement true. N cubed is greater than or equal to n squared plus 3. Right? If we're comfortable with the first one, then the second one is also true. Okay. Then, this is all to show that this inequality is true. So then I'm going to make a function out of this. And I'm going to say my function is x cubed minus the x squared plus 3. And I'm saying that it's greater than or equal to 0 for x is greater than or equal to 2. Right? All coming from that original inequality. I'm going to further analyze here using the derivative. The derivative is 3x squared minus 2x, or x times 3x minus 2. This derivative is positive for values greater than or equal to 2. which means it is increasing. So therefore, f of 2, which equals 1, right? We can make the statement that f of x is greater than or equal to 1. Because f of 2 is 1, f of x is greater than or equal to 1 for all values, for all x values greater than or equal to 2. Okay? Because it's increasing.
Rodriguez,
Yeah.
what does that say, like, above the first derivative, f of what times x cubed?
F of x equals x cubed. You think?
Oh, okay.
Sorry. Yep, f of x equals x cubed.
Thank you.
Yep. All right. So all of that work was just to prove that my first inequality was correct. And that proves it. Now, because I have a true inequality, we know that the 1 over n, right, the summation, the series from n equals 2 to infinity of 1 over n diverges, right? We did that. That was the first example. We integral tested with this. So it's already proven. We're done. Therefore, the larger series also diverges. Okay? So this was a lot of work just to prove that initial inequality, but that's important because there's going to be examples where you can say, all right, no matter, I know that this is true. And then there's going to be problems where you're like, maybe it's not at like these really close values, and then my statement doesn't work out. But all that work led up to the fact that that makes this true, that makes a sub n less than b sub n, and therefore, since a sub n diverged, then b sub n must also diverge.
Wait, what does it say after integral? Sorry.
Yep, this right here says integral tested, right? Like here,
Oh.
I just made that statement because we already did it. And you won't have to in the future, right? We know that that diverges. And therefore, the larger series also diverges.
Did you read the line above? We know that.
I'm sorry. This line says f of 2 is equal to 1. And, right, we prove that we are increasing. So therefore, f of x is going to be greater than or equal to 1 for all x's greater than or equal to 2.
F of 2 is equal to 1.
Yep.
Where do you get f of 2 is equal to 1?
If I just plug it into my original equation that I made up, 2 cubed, 8 minus 7.
Okay, thank you.
Mm-hmm. All right, I'm going to keep going. I know that the bell will cut me off, but I'll make sure that I record the remaining examples before I upload this video, okay? Using the comparison correctly. So study the convergence of this. So this is one of those examples that if we pick the wrong inequality to begin with, it doesn't help us out. So let me show you that wrong situation first. So the summation is 2 to infinity, 1 over n times ln of n squared. So if we use 1 over n, which diverges, right, we know already, but, big but, 1 over ln of n squared is less than or equal to 1 over n. So therefore, this is not helpful.
Is it 1 over ln of n squared or 1 over n times ln of n squared is less than?
Yeah, it's 1 over n times ln of n squared.
Yep, the original again, I'm sorry.
We need the original, not the.
Yeah.
Mhm.
So what we can do is integral test here. It's positive, it's continuous, and it's increasing. It's decreasing, I'm sorry. If I were to derive it. So if I take the integral from 2 to infinity of 1 over x ln x squared dx, all right, my u is ln x, so du is 1 over x dx, that's perfect. So then this is equal to the integral from 2, oops, I forgot to do my u. So u of 2 is ln 2. So then I have ln 2 to infinity of du over u squared, which is just negative u to the negative 1 from ln 2 to infinity. Right, and if I take the limit as r approaches infinity of this, then I'm going to have limit as r approaches infinity. The simplified form with the f of b minus f of a, where r takes place of infinity. I have a negative 1 over r plus a 1 over ln 2. So again, that fraction here goes to 0. I have 1 over ln 2. Which converges, and therefore the series also converges. All right, so I will make sure that I finish. Theorem 5 is the limit comparison test. So again, we have two sequences, A sub n and B sub n, and they are positive sequences. We can assume the following limit exists. The limit as n approaches infinity of A sub n divided by B sub n. So if L is positive, then the series of A converges if and only if the series for B converges. If L equals infinity, then A sub n converges, then B sub n converges. And if L equals 0, then if B sub n converges, then A sub n converges. So take a minute to think about those three different scenarios based on the fact that we are presenting them as a fraction. So example 6, we want to show that the summation, the series, as n equals 2 approaches infinity of n squared divided by n to the fourth minus n minus 1 converges. So we are letting A sub n equal n squared over n to the fourth minus n minus 1, and B sub n equals 1 over n squared. In this case, for large n, right, if we take a look at the degrees of each of these, A sub n is approximately equal to B sub n. So if we take the limit as as n approaches infinity of A sub n divided by B sub n, we would then have the limit of n squared divided by n to the fourth minus n minus 1 times the reciprocal n squared over 1, which is equivalent to the limit as n approaches infinity of n to the fourth over n to the fourth minus n minus 1. And this limit is equal to 1. L is greater than 0. And therefore, since 1 over n squared converges, right, this is, we're following this one here, then b sub n also converges. Okay, last example for this section. So we are going to use the limit comparison test again for the summation from 3 to infinity of 1 over square root of n squared plus 4. We're going to name a sub n the given, and b sub n we're going to use 1 over n for. So if we take the limit as n approaches infinity of a sub n over b sub n, we have 1 over square root n squared plus 4 times n over 1. And if we evaluate this, the degrees are technically the same as we approach positive infinity. Therefore, the coefficient ratio is just 1. And we can make the conclusion since 1 over n diverges. We know this right from the integral test again, from the very beginning. Then the a sub n, 1 over square root of n squared plus 4, also diverges.